So welcome to the first topic in IGCSE Physics, energy transfers. So in this lesson, in fact these three lessons, we're going to look at energy transfer. And these are the learning objectives, which you can read at your own discretion. So just 4 learning objectives, of course, and also an equation to remember. So the first thing we have to say or examine is the concept of energy. So energy is required to do work. So what does that mean? Okay, so in physics, work is applying a force over a distance. Okay, so you need to use energy in order to, say, push a block up a hill. Okay, so when you're pushing the block up the hill, you're applying a force over a distance, and that requires energy. Okay, and we use fuels to release energy. So for breakfast, you would have had some Wheat Bix maybe, or some toast. Okay, and those are fuels. Okay, so your body breaks them down to release energy. And in our universe, the sun is the ultimate source of energy. So all energy comes from the sun. Okay, so for example, the toast was made of wheat. That wheat gets its energy from the process of photosynthesis, and that energy comes from the sun. So there are many different forms of energy, okay, that can transfer between different other forms. Okay, so here are just examples. So you've got thermal energy. So for example, the energy required to release, say, heat from the sun or a fire, for example, that's known as heat energy as well. So those two terms are interchangeable. And that's due to essentially its temperature. So the higher the temperature of an object, the more heat energy it will release. So this volcano, for example, is very hot. It has a high temperature, so it's releasing lots of heat energy. And then we have light energy, okay, and that comes from the energy from something called the electromagnetic spectrum, okay, which we'll look at later in the course. And that's the energy that comes from things like the sun, or from even a simple light bulb, which is working in your room or your classroom. You've got electrical energy, okay, and that is the energy in transferred from, say, a battery into light bulbs, as you can see from the image. And sound energy, which is what you're actually listening now to the video. So what's happening is your computer is creating sound energy, and it's the energy that hits your ears in the form of a sound wave. Another form which is very important, so we'll look at this in more detail, is kinetic energy, and that's the energy from moving. Okay, so this runner, for example, is moving. He is creating kinetic energy. Okay, and there is a calculation or an equation that you will have to become familiar with, but in that equation, basically, the faster you go, the higher your kinetic energy. So as that runner begins to move faster, he will have higher kinetic energy. So it's also called the energy of moving. And that is the equation that you have to start becoming familiar with. EK, or kinetic energy, equals half mv squared. Okay, and the m stands for mass, and the v stands for the velocity, how fast you are moving. So basically what happens is that as the mass of, for example, this runner increases, then its kinetic energy will increase, and also as it moves faster, it will also increase in energy. and kinetic energy. We also have kinetic energy, and that's related to chemical energy, and that's the energy that you'll become more familiar with in your chemistry classes as well, and it's the energy that is released when chemical reactions take place. Okay, so chemical reactions can also incorporate, say you're eating a Big Mac, okay, your body breaks it down into chemicals, okay, that's actually a chemical reaction that releases energy. And the battery actually that we use for the example of electrical energy is also an example of a chemical reaction that releases chemical energy, which is then transferred or changed into electrical energy. And then we also have nuclear energy, so that's the energy from nuclear explosions, which you can see here from the following diagram or image. And this is actually where the sun's energy comes from. It's called nuclear fusion, which we will look at again in more detail as we continue along on this course. Another important form of energy, just like kinetic energy, which we will examine in more detail, is the concept of potential energy. So this is the energy possessed due to where the object is. So for example, a basketball, when it is high up, has high potential energy, and as it falls, it loses its potential energy. Okay, so that's an example of gravitational potential energy. So at the top, the basketball has a high potential energy, and as it falls down, it begins to have a low potential energy. And this is based on the formula, the EP, or potential energy, equals mgh, where it's basically the mass times the acceleration due to gravity, which is g, okay, so this is g here, okay, times the height. So the higher up something is, the more potential energy it has, the heavier it is, the more potential energy it has. So at the top here, if you look at this diagram, this has a very high potential energy at the top of the roller coaster, but as it falls down, it will begin to lower in terms of its potential energy. As what's happening is it's being actually transferred between potential energy into kinetic energy, the energy of movement. And we also have elastic potential energy, so you'll see that with basically elastic bands. Okay, so when you pull an elastic band to its maximum, just before it breaks, it has maximum potential energy, and then you release it, it begins to fall back. It begins to lose its elastic potential energy. Okay, that's the example there. So the next question you could ask is, how do we measure energy? Well, the unit for energy measurement is the joules. Okay, and its symbol is a capital J. So to lift an apple here, okay, upwards, about a meter requires 1 joule of energy. Now it's important too in physics that you get familiar with these little symbols here, like a little k. So the little k means kilojoules, okay? And 1 kilo equals 1,000, 1 kilojoule equals 1,000 joules. Okay, just like 1 kilometer equals 1,000 meters. 1 megajoule, okay, capital M is 1 million joules, etc. Now, an important principle also in terms of energy and energy transfers is the idea of conservation of energy. So this is why it's in red. You need to remember this phrase. Okay? And basically what it's saying is that you cannot create new energy and you cannot destroy energy. So what happens is that energy is being changed into a different form, but the overall energy stays the same. Okay? So when we look, for example, at the roller coaster, okay, at the start the roller coaster had a maximum potential energy, and then over time as it fell down, that potential energy changed into a different form, kinetic energy. But the overall energy of the roller coaster stayed the same. It was just moving between the different forms. Okay, so it also means that inside the universe, if it's a closed system, nothing's coming in, then the amount of energy total in the universe stays the same. That's what constant means. It just means it stays the same. So we look at this example here. This is the example of a pendulum. Okay, so a pendulum basically is a mass at the end of a string. Okay, and we start to move it back and forth. Okay, so here the pendulum is at a maximum. Okay, you release it. Okay, it has, at the beginning, it has high gravitational potential energy because it's got a maximum height. Okay, and the kinetic energy at this time is going to be pretty close to zero. Okay, so now we're going to release it. Okay, so it goes into the center, and now the gravitational potential energy has gone because now the height is zero, and now the kinetic energy, because it's moving, is at a maximum. And then as it begins to move up again against gravity, the potential energy begins to increase because again the height begins to increase, and the kinetic energy moves to zero, which makes sense because when you do the pendulum, what happens at the end is it stops moving at this point. Okay, and remembering that kinetic energy is half mv squared. If v is zero, then kinetic energy will also be zero. And we go back again, goes back again, the gravitational potential energy is a minimum because height is a minimum, and it's now at a maximum for kinetic energy because this is where the speed or velocity of the object, the mass, is at its maximum. And finally, go back to its original position. The height's increased, the gravitational potential energy is now at a maximum, and it stopped moving, so the kinetic energy is zero. But overall, the energy, the total energy, which is the gravitational potential energy plus the kinetic energy, stays the same. Energy is neither created nor destroyed, it just moves between gravitational potential energy and kinetic energy. And that's the equations there. Okay, so and this of course assumes there's no air resistance in the system, but there of course is. So this is maybe when there's a vacuum. It's an ideal system, which we tend to like to use in physics. And you can see the equations there for E total, EP, and EK, the potential energy, the kinetic energy, and the total energy of the entire system. And it's interesting, we didn't really discuss air resistance because that can link quite clearly between useful and wasted energy. Okay, so in physics, useful energy is given the following definition. Okay, so it's basically energy that we want to use, and therefore if we have energy we want to use, any other form of energy that doesn't fit within that definition is considered wasted energy. And what happens to that energy is it spreads out to the universe. Okay, so think about, for example, a light bulb. Now, obviously, if you touch the light bulb, it's going to be hot. That's wasted energy. So we really want the light bulb to basically release light. Okay, so there's light energy and there's heat energy. That heat energy is wasted and it spreads out into the surroundings. Oh, and there we go. So that's the example there of heat energy. And this therefore is related to how energy efficient objects are. So for example, if you have a light bulbs have an energy efficiency rating. Okay, and it's basically how much energy is used to form useful energy. Okay, so for a light bulb, that'd be how much of the energy of the battery would be used to actually go towards making light rather than making heat energy. And this is the equation for efficiency, which you have to know. There is the useful energy output. So for example, for the light bulb, that will be the amount of light energy that's being released divided by how much energy actually went into the light bulb. Okay, and because of this, the overall efficiency of an object, like for example, a light bulb, can be no greater than 1. If you have an efficiency of 1, that means that the useful energy output equals the total energy input. So all the energy going in is being used usefully. Okay, and that's the example there I've used, energy efficient light bulbs. Okay, so in the energy efficient light bulbs, which I'm sure you have at home, what happens is that more of the electrical energy that's being put into the light bulbs is being used for light, and less is being used to be wasted as heat energy. And we can use this value in terms of a percentage efficiency. Okay, so basically we calculate our efficiency and then multiply that number by 100. Okay, and the higher the number, the more efficient it is. So if you have two light bulbs and one is at 95% efficiency and one is at 80% efficiency, then we say the one at 95% is more efficient than the one at 80%. And again, because efficiency can be no greater than 1, the overall efficiency of an object or a device is 100%. Now, there are many ways to improve efficiency, because obviously we have these efficient light bulbs. So in terms of light bulbs, as our example, the main wasted energy is that of heat, and we can decrease the loss of heat by using oil as a lubricant, for example, in mechanical devices. We can reduce resistance, which we'll look at later in the course as well, concepts of electrical resistance in circuits. And we've already looked at the pendulum, so we can actually reduce the amount of air resistance, for example, of a pendulum by using a more streamlined shape on that object. So in our first example, the object was a sphere. We could change that to a more streamlined or aerodynamic shape to reduce the effect of air resistance. Okay, and we can also reduce the loss of sound by tightening loose parts of machinery. So for example, outside at the moment, you cannot hear it because I'm using my headphones, but we have a jackhammer going. It's very noisy. So one way they could reduce this amount of energy being wasted to sound rather than actually in the jackhammer could be to tighten the loose parts of machinery. So we can also illustrate this efficiency by something called an energy flow diagram, also known as a Sankey diagram. So this is the general diagram. So you start off with the device that you've got. So it could be a light bulb or a jackhammer or a speakerphone, for example. And then we have the energy going in and the energy going out, which is useful, and the energy going out, which is wasted. So basically three things. Okay, so we've already looked at electrical light bulbs, so we use this as an example. So here's our object, the electrical light bulb. So we put the light bulb in the center because that's the device. We have the electrical energy going in from the battery or the mains electricity. We have the light going out, and then we have our wasted, which is probably going to be heat. Okay. A microphone could be another example of a device or an object. So you put the microphone in the center, the input going in, which is your sound energy from your voice, la 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 la, and then the output would be the electrical energy going to your speakerphones or speakers, and then also the wasted energy would be in the form of heat energy. Car engine would be another case in point. So we've got the car at the start. We have chemical energy from the fuel, okay, from the petroleum that you're using to power the car, or if it's an electrical car, electrical energy. Then we have we basically want the car to move, so the useful energy is the kinetic energy of the car moving, and wasted energy could be sound, for example, or heat energy. And for those biologists amongst us, we have the concept of photosynthesis. So we put the plant in the middle. The light energy from the sun is your energy input. Useful energy is going to be the chemical energy the plant's going to use to grow, and then the wasted energy will be the heat energy associated with it. And we can extend that further with a more detailed diagram called a Sankey diagram. And a Sankey diagram is basically a energy flow diagram like we've shown, but it's just a bit more stylized. Okay, so we put the device in the center. We have the input, and this time it's a really big fat arrow, and then we have the useful output, and the wasted output. Now, in the Sankey diagram, what happens is that the size of the arrows, okay, so size of these arrows here, okay, determines how big those values are. Okay, so you'll notice for the input, it's a rather big arrow. The useful output's a bit of a smaller arrow, and then the wasted output's a bit of a smaller arrow as well. Yeah, so basically the width, which is this part here, is an illustration of how big the energy is. So lots of energy going in, some useful output, and a lot actually going to wasted output. And also remember that the wasted output always goes down. The useful output is always kind of in the same line as the input. And here is just some online simulations you might like to try. Okay, there's a whole range of possibilities there, which are found on the PowerPoint which goes along with this video. So thank you for listening.